Hello Year 12 and welcome to the last video here for this topic, natural growth and decay. Now we call it natural growth and decay because many natural phenomena follow these sorts of rules. That in many cases, let's say it's a population or some sort of quantity increases at a rate that is proportional to the population. All right, if we're talking about the number of rabbits on an island, and we will because, that's how these questions tend to go. Talking about the number of rabbits on an island, right? The rate at which the population is increasing depends on how many rabbits there are, right? How many rabbits are there affects how quickly they increase. How quickly they increase, of course, affects how many rabbits there will be. Now, that means that the rate of change is proportional to or equal to some constant multiple of the population. Right, so K is some sort of constant. We know that this is true. Now, when do we see this sort of relationship happen? When the derivative of some function is very similar, right, is some multiple of the function. That we have seen occurs when we have exponentials. Okay, so for some quantity, right, some quantity is equal to this initial quantity times e to some constant by time. If I differentiate this, I get k times the initial value. I get k. So let's have a look and see how that works. Sometimes when it is decay, right, if it's going down instead of up, we could either work out a negative value of k or we have negative k, right? One way or the other. Doesn't make a big difference, but remember this, we end up with a situation where the rate of growth or decay is proportional or depends upon the size of the quantity or the population. We're going to use, just stick with this formula here. If it's decay, you can put a negative in there, but it really doesn't make a big difference. So let's see how this happens. We have population here, 95. We've got our initial value here. So this is PO is equal to 1,000. P0 is equal to 1,000. I know that 5 years later, my population has climbed to 3,000. And we're told that population growth, law of natural growth, this tells us that it's not at a constant rate, right? I don't just look at the gradient between here and there and assume that it's going to be the same all the way along. No, I know that it's going to follow this sort of a pattern here. Right? Show that it satisfies the equation. Well, if that is the case, if P equals P0, which is some constant, e to kt, then dp by dt, differentiate this, and I've got an exponential. I get is k times p0 e to the kt, which is equal to kp. Oh, this is supposed to be a kp here. It's another typo. Equals kp as required. Okay, here we go. We've shown that dp by dt equals kp. Also, I should also just explain that this one here. Now let t equals 0. Therefore, p equals, no, because I do have to show this in the same. P equals P0 times e to the 0. Therefore, P equals P0 when t equals 0. So that establishes that P0 is the initial value. Okay, we probably need to do both of those things to show that this equation here satisfies this one here. Now, find these things given that information that we got at the beginning. So, we know that my population, I'm going to say 3,000, is equal to, P0 was 1000 times e to the k, and t is equal to 95 to 2000 to the 5. There we go. Now I'm going to rearrange things here. I'm going to say e to the 5k, e to the 5k equals 3000 and 1000 equals 3. Now take the log of both sides. I'm going to say 5k equals the log of 3. That means that k is equal to 1/5 times the log of 3. Alright, you could say it's 3 to the 5th. That's the 5th root of 3. A 5th times the log of 3 will be fine. So we've got, well, I found PO, and now we've got K. So now I can say that P is equal to 1000 e to the 1/5 of 3 times t. Right, that is my graph. Now if I am to sketch this, this is going to be t here, is my independent variable, and this is going to be p. And what's happening is I'm going to start at 1000, right, because p0 is equal to 1000, and then it climbs exponentially. Like this, something along those lines. Okay, wonderful. Moving along, how many rabbits would be at the start of 2003? This is going to be t equals 8. So my population is equal to 1000 times e to the 1/5 times the log of 3 all times 8. All right, into the calculator. Clear. Now we haven't used this e to the power of terribly much, I don't think. Let's second function. Here we go. E to the power of 1 divided by 5. No, let's not do it that way. I'm going to say, if you don't mind, 0.2. Right, you put a factor in there or something. 0.2 times the log of 3, close my brackets, times 8. You okay with that? Equals, multiply that by 1000, equals 5,800. Looks pretty good to me. Rabbits. Build a wall to keep the rabbits out. How many rabbits will there be instead of 2003? 5,800 rabbits. That sounds pretty good because, you know, we saw that a few years ago it was 3,000. Yeah, that's increasing at a reasonable rate. Now, when will the population be 10,000? Okay, well, 10,000 equals 1000 times e to the 1/5 log 3 times t. Now this means that e to the 1/5 log 3 by t equals 10,000 on 1000 equals 10. Log of both sides, that means that 1/5, that's the log of 3 by t equals the log, natural log of 10. I take the log of both sides. That means that t is equal to the natural log of 10 on the 5th of the log of 3. In fact, I could say, you know what, I'm going to rub that a little bit out because I don't like fractions. I'm going to say 5 log 10 over log 3. Okay, t equals 5 log 10 on log 3. All clear. 5 log 10 equals, divided by the log of 3, is equal to 10.5. It's pretty close to 10.5 to the nearest month. Equals 10.5 years, or 10 years, 6 months, is going to be 95. So 2005, I'm going to say it is equal to 1 month. So I'm going to say probably around July 2005. All good? Righto, that is the very end. We didn't look at a decay, but there's some other examples there, and frankly, it's been going on for quite a while now. Hope they're helpful. Of course, I will see you in class. Maybe I'll see you on a Wednesday, or shoot me an email and I'll do my best to get back to you. Thanks, guys.